In our last video, we built the engine of modern AI, the scaled product attention. We saw exactly how a word calculates its relationship with every other word in a sequence using vector geometry. But there is a critical flaw in what we just built. The architecture we coded is called single-head attention, and it suffers from a massive structural bottleneck, a phenomenon we can call vector collapse. Imagine you are analyzing a complex paragraph. If you only have one single attention mechanism, that mechanism is forced to average out all the different types of context into one single vector. But human language is not flat. A single word contains multiple, overlapping dimensions of meaning. Look at the word bat. In one sentence, it is an animal. In another, it is a piece of sports equipment. Look at the word apple. It can describe a technology company, or it can describe a piece of fruit. If our neural network only has one perspective, it has to compromise. Think about the mathematics of this compromise. If it takes the mathematical vector for fruit and literally averages it with the mathematical vector for technology company, what do you get? You get a vector that means absolutely nothing. It points nowhere. It becomes mathematical noise. A single attention mechanism becomes a bottleneck of nuance. It is like trying to understand the plot of a complex, 3-hour movie by only looking at the color grading and completely ignoring the dialogue, the soundtrack, and the actors. You might get the overall mood, but you lose all the critical, high-resolution details. To solve this problem, the creators of the transformer architecture did not just stack more layers on top of each other. They did something much more elegant. They split the brain of the network into parallel processing units. Today, we are stepping up from basic tutorials. We are going to code the true architecture of GPT models. We are building the multi-head attention mechanism from scratch. Think of multi-head attention not as a single isolated genius, but as a highly specialized board of directors sitting around a table. When a prompt enters a large language model, every single token is projected into a massive, high-dimensional vector. Let's call this the D-model dimension. In early models like the original transformer, this vector was 512 numbers long. In modern models like GPT-4, it is in the thousands. Instead of forcing one single attention mechanism to process all 512 dimensions at once, we slice that massive vector into smaller, parallel segments. If we configure our model to have 8 heads, we divide our 512 dimensions by 8. Each head now receives a chunk of exactly 64 dimensions. This is where the magic happens. We project the data into different, specialized mathematical subspaces. During the training phase of the neural network, these heads learn to specialize automatically through backpropagation. Nobody explicitly programs them to do this. Head number 1 might dedicate its 64 dimensions exclusively to tracking grammatical syntax, constantly scanning for verbs that connect to the current subject. Head number 2 might focus entirely on identifying emotional sentiment or hidden sarcasm. Head number 3 might strictly look at the chronological order of events, ensuring the logic flows forward in time. They all read the exact same input sentence, but they extract completely different features. They perform their products independently, ignoring what the other heads are doing. Then, at the very end of the process, they concatenate their independent findings back together into a single, unified vector. This architecture totally prevents vector collapse. It gives the AI multiple, simultaneous perspectives on the exact same data, preserving all the rich, contradictory nuances of human language. Let's look at the mathematics of why this is considered an absolute engineering masterpiece. You might ask, why slice the dimensions at all? Why not just run 8 full-size attention mechanisms in parallel, each processing all 512 dimensions? The answer is computational cost and memory bandwidth. Matrix multiplication is incredibly expensive. It scales cubically. If we ran 8 full-size attentions, the memory and computational requirements would be devastating. Running these models locally on a standard machine would melt your hardware. By dividing the D-model dimension by the number of heads, the total amount of computation remains roughly identical to a single head attention layer. We get 8 times the perspective for the exact same computational price. We define dk, the dimension of the keys and queries for each head, as D-model divided by the number of heads. 512 divided by 8 gives us 64. But there is one crucial detail we cannot skip: the linear projections. If all 8 heads receive the exact same slice data, they would all output the exact same attention scores. That would be useless. To force them to learn different things, we multiply our inputs by specific weight matrices before calculating attention. We call these WQ, WK, and WV. Imagine these weight matrices as polarizing filters on a camera lens. They transform the raw words into the specialized queries and keys needed for that specific head. These weights are the actual parameters the neural network learns during training. Finally, after all heads compute their attention, we take their outputs, concatenate them back into a single 512-dimensional vector, and pass them through one final linear projection matrix called W output. This final matrix mixes the insights from all the different heads together into a final conclusion. Let's stop theorizing. Let's open Python and translate this entire architecture into clean, executable code. We will use pure NumPy to keep the logic completely transparent. No black boxes. We start by defining our class, multi-head attention. In the initialization method, we set our default parameters. D-model is 512. The number of heads is 8. Next, we calculate DK. We do this with floor division, dividing D-model by the number of heads. This ensures our dimensions divide perfectly without leaving remainders. For our defaults, DK will be exactly 64. Now we define the brain of the layer, the weight matrices. We need weights to project our queries, keys, and values. We initialize WQ, WK, and WV as random matrices. Notice their shape, D-model by D-model. In a real network, these random numbers would be optimized through gradient descent. We also initialize WO, our final output projection matrix, which will mix the concatenated results at the very end. This setup gives us the foundation. Now, we need to write the forward pass. The forward pass is where the matrix manipulation gets intense. First, we create a helper function called split heads. This is the core mechanic of the architecture. We take our input tensor and we use NumPy's reshape method. We tell NumPy to take the massive D-model dimension and break it into two separate dimensions, number of heads and DK. But reshaping is not enough. We must transpose the matrix. We swap the axes so that the number of heads dimension sits right next to the batch size. This specific alignment allows NumPy to perform the matrix multiplications in parallel, treating each head as an isolated batch. This is the secret to the GPU speed. Inside the forward function, we execute the steps. Step 1. We multiply our input matrix X by our weight matrices to generate our raw queries, keys, and values. Step 2. We pass them through our split heads function. Now, instead of one massive matrix, we have 8 independent matrices ready to be processed. Step 3. We perform the scale.product attention. We multiply Q by the transpose of K and divide by the square root of dk to prevent vanishing gradients. We apply our stable softmax function to get the probability weights. Finally, we multiply those weights by our sliced value matrices. We have the outputs from all 8 heads, but the next layer of the neural network expects a single continuous vector, not 8 fragmented pieces. Step 4 is the recombination. We transpose our attention output back to its original layout, and we reshape it. By flattening the last 2 dimensions together, we perfectly concatenate the 64-dimensional vectors back into a massive 512-dimensional block. Step 5. We pass this concatenated block through our WO projection matrix. Let's run a simulation in the terminal. We will feed the class a dummy input representing a batch of 2 sentences, each 3 words long, with a dimension of 512. Look at the output shape in the console. The output shape perfectly matches the input shape. The tensor enters the layer, gets sliced into 8 parallel dimensions of meaning, gets mathematically evaluated, stitched back together, and exits ready for the next block. This is the exact multi-head attention logic running inside GPT right now. In our next video, we will wrap this mechanism inside the residual connections and layer normalization that make deep learning possible. Subscribe, check the code on GitHub, and I will see you in the next one.